So question 10 asks us if the pH of this solution will either be above 7, 7, or below 7. So we know this is a salt, and the salt comes from the cation of a base and the anion of an acid. So the cation in this salt is Na, the anion is NO2. Since the cation had to come from a base, we know that the base that from which the cation came is NaOH. Since the anion came from an acid, to make it an acid we need an H in front of it, so it's nitrous acid. Is this a strong or a weak base? So it would be strong because it's in group 1. Sodium's in group 1. So hydroxides of group 1 and group 2 elements are strong or make strong bases, except for beryllium. But this is sodium, it's in a group 1, and it makes a strong base. For acids, we said you could say that they are weak if the oxygens minus the hydrogens is 2 or more different. So this is 2 minus 1, so the difference is 1, so therefore that's a weak acid. So a salt of a strong base, weak acid, creates a pH that's above 7. You can think of it as the base is strong, the acid is weak, so we're going to go to the strong side, and that's the basic side, so it's going to be greater than 7. Number 11, a solution contains 0.2 molar acetic acid and 0.2 molar sodium acetate. Which substance reaches equilibrium? This is a salt. It's a soluble salt, so it's going to come apart like this. Acetic acid, though, is an acid. It's a weak acid. Hg2, H3O2. I'm going to use Arrhenius definition because of space here. So this one goes to equilibrium because it's the acid. The salt is soluble, no equilibrium. The acid is a weak acid, and it will hit equilibrium. So HC2, H3O2. What's the hydrogen ion concentration in the buffered solution? Well, that's a little harder question. So we're going to take this acetic acid. I'll go ahead and write the full equation. Bronsted-Lowry definition. All right, so we can see we hit equilibrium here, and we'd have acid, base, conjugate base. We know the original concentration of the acetic acid is 0.2. So if we ice it, ICE, that's 0.2. We know it's going to go down by X amount. We know on this side it's going to go up by X amount. We didn't have any of this to start with. However, since we had this 0.2 molar sodium acetate, then that means this all goes away because there's no equilibrium, so we got 0.2 and 0.2. So the original concentration of the acetate ion is 0.2 molar, and that comes from, these two guys being the same ion. They're common. They have that ion in common. So since that's 0.2, originally we had 0.2, it goes up by X amount, and at the equilibrium we would have 0.2 minus X, X, and 0.2 plus X. So now to set up the equilibrium expression, we know that Ka is going to equal the hydronium multiplied by the acetate divided by the acetic acid. All right, the ionization constant, I hope I gave you somewhere else on this little practice sheet, but I might not have. Oh, it did. Right here it is. So acetic acid is 1.75 times 10 to the negative fifth. So we would say 1.75 times 10 to the negative fifth is equal to the hydronium, which we know is X, multiplied by the acetate, which we know is 0.2 plus X. Now once again, this 0.2 originated from the sodium acetate salt that was dissolved in the water. And then on the bottom we've got the concentration of the acetic acid, which is 0.2 minus X. Now remember that little rule that you might be able to ignore these minus X and plus X? So this is 5, negative 5. This is 2 times 10 to the negative first. I'll go ahead and write it down. 2 times 10 to the negative first. So if this exponent and this exponent are 3 or more apart, you can ignore the minus x. Same thing for the plus x. This is 2 times 10 to the negative first again, and yet they're more than 4 apart. The exponent's more than 3 apart. And you can ignore the x if it's 3 or more apart. So we can ignore this x by that rule, and we can ignore this x by that rule. Now what is 0.2 divided by 0.2? Isn't that just 1? So they cancel out too, don't they? So there we go. Cancel that out. That was ignored. So now 1.75 times 10 to the negative fifth is equal to x. So x equals 1.75 times 10 to the negative fifth. So that's your answer right there. Sorry about that. So this answer goes right there, 1.75 times 10 to the negative fifth. Okay, now is the pH of the acid and salt mixture greater or smaller than the pH would have been if the salt hadn't been added? So when I added this salt, that caused an increase in that, which caused the equilibrium to move this way. If equilibrium goes left, what happens to the hydronium ion concentration? Right here. Will it go up or down? Well, it's going to go down, isn't it? So this is our initial stress. Equilibrium shifts that way, so this has to get used up to make more of this. If this goes down, that means less acid, because this is the ion that makes acid. So if there's less acid, what happens to pH? So the pH of the mixture would have been higher. I think we have one more time to do one more problem here. So this one is a stoichiometry problem. You have 40 milliliters of 0.2 molar sodium hydroxide and it's completely consuming 25 milliliters of HCl. So we're going to go ahead and write the equation. NaOH is going to react with HCl. It's going to make sodium chloride, and the other product is water. We have 40 milliliters. Can I assume that you know that that's 0.04 liters? And then there's 0.2 moles per liter. So we have 0.008 moles of sodium hydroxide. Since it's a 1-to-1 ratio, I'll go ahead and write it all out. So NaOH doesn't have to be a 1-to-1 ratio, but it is in this case. But anyway, so we'll put moles of NaOH down here. Whoops. And we'll put moles of HCl on top. It's 1-to-1. So that gives me 0.008 moles of HCl. Now if we want to know the concentration of the HCl, that's what it asks for, right? Concentration in moles per liter. We know how many moles. We just have to divide by the number of liters that we had. So how many liters do we have? We have 25 milliliters. If I divide that by the number of liters, which is 0.025 liters, I would get the concentration of the HCl. So 0.008 divided by 0.025, 0.32 moles per liter. So 0.32 molar. All right, this next problem is kind of involved, so I'm going to make those in a separate video. And right now, I'll get that done after school today. So I guess that's it for this one.